please welcome Broadcom Senior Vice President and General Manager, Core Switching Group, Ram Velaga.
Good morning, and welcome to OCP 2023. The title of my presentation is Paths to Singularity. Now, it's a play on words. For those of you who are paying attention to the whole AI space, singularity refers to a state where the capability of the machine is equals to the capability of a human mind, or in some cases even transcends it. Now, when you think about can we get there, the compute that we need is far more than you can put on a chip, a chiplet, multiple chiplets connected by an interposer. None of that is sufficient. You're probably talking about tens of thousands of nodes, if not hundreds of thousands of nodes that need to be connected together. And when you connect these things together, there's a network that is needed. And I've said this before last year, and I'll say it again. Network is the computer, and that's what we're going to talk about the course of this next few minutes. But before I get started, I do want to take a minute to thank the OCP community. First, for all of you who are here from all around the world, thank you for attending. Over the last decade or so, Broadcom's made many contributions to the OCP community. Obviously, for us, it's a self-fulfilling need to contribute to the OCP community because we are a chip maker. We don't build systems, and we really rely on the ecosystem around us to be able to build these systems, hardware, software, cooling systems, and so on and so forth. And the only way we are able to succeed is by actually having our products, our specs being available to the OCP community. And we really appreciate the support and the environment that you've provided for us to be able to do what we've been able to do. And coming back to, this network is the computer. Right? If you look at Moore's law, I think there's no debate at this point that Moore's law has diminishing returns, or at least probably reached a point where you really don't get any benefit from going to successive process nodes, other than maybe some power reductions. But the cost per transistor is going up. But at the same time, the need for computational capacity is increasing exponentially. So how do you then solve this problem where your chips are not getting any larger, the performance is not substantially increasing, but you need many thousands of these nodes, whether they're compute nodes or accelerator nodes, to be able to perform a job function, right? And to be able to do this, you need a network that connects them together so it forms one single large system. So hence, this whole idea that the network is the computer, it's not new. Sun talked about it almost 20 years ago, and we continue to very strongly believe that the network is a fundamental element of scaling compute. Now, the other thing that we've also postulated last year was the network is the compute, but what is the network? And we said, look, Ethernet is the network. It has been the network for cloud computing in the past. It is the network for ML AI today, and it will be the network for ML AI tomorrow in terms of the scale that is needed, right? And we said this actually last year at the OCP, which was in October 2022, before the world kind of got introduced to this whole concept of ChatGPT that happened in November, December of last year. And then you look at what happened in Ethernet over the course of the last year, right? The one thing on the Ethernet is what we all believe in here, which is Ethernet's based on open standards, a very open ecosystem. It's plug and play, it's interoperable. You have a lot of different players in the Ethernet market. Last year, we talked about how there was 600 million Ethernet ports shipped in a year. When you look at all of this, there's a lot of economics and economies of scale in Ethernet. And to make the point about the economies of scale in Ethernet, there's a few data points I want to highlight. First, Ethernet is 50 years old. Actually, I should probably say it's 50 years young because it seems to be getting better with age. Two is the inventor of Ethernet, Mr. Metcalf, won the prestigious Turing Award for the contributions to the world with what Ethernet is able to provide. But outside of these milestones for Ethernet, just over the last year, if you look at the number of vendors that have actually announced high-performance switches to serve the needs for ML AI bandwidth, is amazing, right? You've got Broadcom that's announced a couple of switches almost about a year ago, followed that by other vendors such as Marvell and Cisco, who most recently introduced their 50 terabit switches. But the beauty of this is more than anything else, those who previously were pushing other technologies such as InfiniBand, they themselves have also come and announced Ethernet switches, specifically focused on ML and AI. And that's a beautiful thing, which is the power of the Ethernet, which is we have multiple different vendors all providing an open, standards-based high-performance network to be able to scale both for today as well as the needs of tomorrow. On that note, the one thing I do want to bring out is at every one of these OCP sessions, Broadcom, we talk about a brand new switch that is just coming out. We just announced it today. This is called Qumran 3D. It is the world's most powerful single-chip router, and that's the most power-efficient device that you'll find there for about 25 terabits, with the power of the entire chip being less than 700 watts, right? What this does is Ethernet continues to scale with economies that no other technology can provide. Now, you don't have to take my word for it. If you just look at the largest operators in the world, all their ML AI infrastructure is connected over an Ethernet fabric, right? And when I say this, there's questions that come back. This is what I call the second-order derivative question. Somebody will come and say, is this the front-end network? Is the front-end network on Ethernet, but is the back-end on something like InfiniBand? No. This is just one single network. It's Ethernet. The front-end, the back-end, they all converge into one fabric. It's an Ethernet fabric. We're talking about tens of thousands of AI nodes, if not much larger numbers, all connected over an Ethernet fabric today, right? So make no mistake, Ethernet is deployed at scale at the largest, operators in the world, and it will continue to get deployed. Why? Because it's very simple. Because Ethernet has an ecosystem that no other technology has. You have troubleshooting, you have testing equipment, you have, monitoring equipment, and you have the ability to be able to remove one vendor's switch and replace it with another vendor's switch, or replace one vendor's NIC with another vendor's NIC, and everything should work together. That is why Ethernet is so ubiquitously deployed today, as well as what we believe is going to go forward. Now, you look at all of this and say it's great. You've got Ethernet today. With technologies such as Rocky over Ethernet, you can scale to tens of thousands of nodes. But what happens as we look ahead? If you look ahead, if you just look at the pace at which these language models are growing. In 2020, ChatGPT-3 had about 175 billion parameters. ChatGPT-4 is supposed to have more than 1 trillion parameters, right? So whether these are large language models or recommendation models, what you see is there is a significant scale of resources which are needed to be able to handle the next generation of these models and the evolution of these models. So when we talk to a lot of these operators who are building on these models today and what they're planning on building going forward, the question that comes back to us is, can we have a network that connects hundreds of thousands of nodes? Okay, now suspend your disbelief for a minute. Can you actually cool these things? Can you put them inside a data center? Can you have enough optics to run them? All the other questions that others have brought up in the meeting on this presentation so far. But I would always say, suspend your disbelief, make sure you do what you can to the best, and somebody else will solve the bottleneck another day. So if you ask the question, how do you scale to 1 million nodes? And that's what's being asked, can we get there? And I promise you, that is the question that most customers or vendor and partners that we talk to are trying to solve. And so with that as a backdrop, how do you scale to hundreds of thousands or millions of nodes going forward? About a couple of years ago, a group of players in the industry got together with the goal of achieving 3 things. 1, Ethernet has the performance of a supercomputing interconnect. I want to repeat that once again. Ethernet has the performance of a supercomputing interconnect. 2, it needs to be done at scale. When we're talking about scale, it's not tens of thousands or a few hundreds. We're talking about hundreds of thousands, right? Scales of 100,000. Number 3, it needs to have the total cost of ownership and the ubiquity of Ethernet. They said, if you establish these 3 as the goal, knowing what Ethernet's already doing today, which is tens of thousands of compute nodes, but going to 1 million nodes, what needs to happen to Ethernet? So as you look at the names on this list, right, these are companies that know how to do compute. These are companies that know how to do networking. And these are companies that have deployed some of the largest cloud-scale networks in the world and systems in the world. They've come together and said, let's actually figure out what needs to happen on Ethernet to improve Ethernet, not because it's not great today, but because of where it needs to be in 2 to 4 years from now, right? And hence the Ultra Ethernet Consortium was formed. with the singular goal of an Ethernet extremely high performance, extremely high scale, at the best economics that any interconnect can offer in the world. And so when you look at that and say, OK, so give me an example of what they were able to do in this space, specifically, we said, OK, let's focus on RDMA. As you know, RDMA is probably one of the most fundamental technologies that allows for memory transfer from one piece of compute node to another piece of compute node. It was built generally with InfiniBand in mind. And over a period of time, RDMA was evolved to be able to support RDMA over Ethernet, which was called Rocky. And Rocky and RDMA work perfectly fine, and Rocky works fine today for many thousands of compute nodes. But the problem is the following. When RDMA was built 20 years ago, the idea was that they were going to be able to connect one node to another node, and then maybe it went from a dozen node to another dozen nodes, and maybe it went from 100 nodes to 200 nodes, because most of you will probably remember, not long ago, HPC clusters that an enterprise customer or even a large oil and gas exploration would buy would have 256 nodes, maybe 512 nodes, maybe maximum 1,000 nodes, right? That's what RDMA was built for. But today, if you go and talk to somebody about 1,000 nodes, they'll say that's child's play. Even 10,000 nodes has been there and done that. 100,000 nodes and more than 100,000 nodes are what people are interested in. So then you say, well, what's the problem with RDMA? RDMA wasn't built for that kind of scale. There's a bunch of assumptions that RDMA made in the past. There's no multipathing. That is, I can only take one path from point A to point B, and all the traffic flows on that one path. That means I might have a link that is completely underutilized and another link that is super utilized, right? There's the idea of an in-packet delivery. That is, all the packets in a flow have to be arrived. One has to, 2 has to follow 1, 3 has to follow 2, 4 has to follow 3, and so on and so forth. And one of these things, like go back N, what that means is, in an RDMA flow, if I dropped a packet, let's say I dropped a packet 5, but I delivered packet 6, 7, and 8 perfectly fine. Go back N basically means, hey, you dropped packet 5, so I want you to retransmit packet 5, 6, 7, and 8, 9 all over again. That is super inefficient, right? And it was also based on the idea that there was a lossless network that was based on DC/QCN, not based on TCP/IP, which was very, very much more robust. So what happened was you had a very fragile network. You had to super engineer it. Somebody who sold you the system would probably want to sell you everything from the optics to the cables to the systems and charge you like 10 times more than it should be charged. So there's a whole bunch of things that has served the existing marketplace well, but it's not suited for where the world is going forward. And that's when Ultra Ethernet said, hey, look, let's solve this RDMA problem. Let's call it the Ultra Ethernet Transport. And we do a bunch of things. Everything that I said was bad here is going to be fixed in the future. And that's what they're working on without spending too much time on a line-by-line item, right? Net, the idea is you have a very high-performance network, removing all the inefficiencies of legacy RDMA so that you're able to scale to 100,000 plus nodes in a network that is extremely robust. Because one thing in a supercomputing job that is extremely important is if you drop a packet, and there was actually a paper that Microsoft published, that even 0.1% of packet drops causes an exponential increase in job completion times because you have to go back to the state where the packet was dropped and the whole job has to be run all over again. Super inefficient, right? So the idea is a very robust network that's done at scale, high performance, and open standard space. So that's what the Ultra Ethernet Consortium is doing. The initial founding members, it's now been opened up to a whole bunch of other companies. We have an interest list of over 200 companies that are interested in joining the Ultra Ethernet. So all said and done, what I want to close with is the following. In the world of ML AI, it is not going to be one company that's going to provide the GPUs or one company that's going to provide the interconnect. The only way we're going to be able to scale is to have an ecosystem of many vendors providing accelerators. And the only way such an ecosystem is going to survive is to have an interconnect fabric that is open, based on standards, high performance, the best TCO that you can get, and there's no alternative to Ethernet, either today, in the past, or where we're headed to tomorrow. Thank you very much for your time, and enjoy the rest of your day.